Hi, this is Farhan from AlgosFromScratch, and I welcome you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. In this video, we are going to work on the training loop where we will be training our model. So in our last video, we completed our model. We combined every individual part. Now we have something you can say a model, a box you can say. Okay, this is our model. This model has weights, biases, okay, weights and biases, etc. So these weights are now randomly initialized. In this video, we will pass this model through a training loop. What we do in this training loop, we pass our model, we ask our model to predict something on any example. Okay, so our model gives us logits. Okay, then we calculate the loss on those predicted values. Okay, and on the basis of this loss, we then update these weights. Okay, so these weights, by the end of this training loop, we will have the updated weights, not these randomly initialized weights. Okay, so this is the flow of a general training loop. In this, we start with the batch. Okay, so we extract a batch from our training examples. We pass these training batches, like we do not just pass a single example at a time. Okay, we pass a batch of either 16, 32 or 64, something like. We first of all extract these batches. Okay, each time a batch is extracted and it is passed through the model. Okay, and the model then predicts on this and the weights get updated. Okay, this is where we just call this optimizer dot zero grade, because PyTorch accumulates the gradients. Okay, so with this we just reset the gradients to 0. Then we pass the data through this forward pass. Okay, and in this forward pass, let me just zoom it a bit. In this forward pass, we basically calculate the logits. So we will be calculating logits, and these logits along with the original labels, we then pass to the loss function. Okay, over here. Here we calculate the loss. Okay, like the loss function will be checking the predicted values against these original labels. Okay, so let's say originally we have a sentence that is from the 0th class. Okay, so it will then check if it has been predicted correctly. Okay, and on the basis of that it will calculate the loss. Then we just execute this backward pass where we calculate the gradients and just keep them. Okay, and this optimizer dot step then takes those values and update the gradients or the update the weights. Okay, this simple flow we will follow. Okay, and these are some steps that we are going to follow in this training loop. Okay, so we will tokenize the data set and clean it. Okay, then we will set the format for the tokenized data set. We will set the format to torch tensor. Okay, and then we will prepare the data loader and test it. Okay, and we will then prepare the loss function and the optimizer, and then we test it on a single batch, and finally we will start our training and evaluation loop. Okay, let's just move on to the coding screen. Okay, we're here. This is our same notebook. Let's just check the run type. We need to use the GPU for this because we will be training our model. So I'm going to just save it. Okay, and now you can see here I'm just executing all those installations and importing, and then these model and tokenizer downloading it. So this all we have already done this in our very first video, I think, where we just fine-tuned our uh, DistilBERT model using the Hugging Face transformer. So I'll just simply execute this. This is our data set. We will be using this data set. We have already worked with this. Okay, so the model and the tokenizer have been downloaded. Okay, now we will also download the data set. So this is our data set, and now here is our custom code part. Okay, so this is our model config where we have all of these configuration values. Okay, we use them in the custom classes. Okay, I'll execute this, and this is the embedding class. Okay, so the embeddings layer, we have tested it, we have worked on this, okay, properly. So I'm not going to test them. Okay, this is the knife classifier. I don't need this. Okay, the single head, I am not again going to execute this because I don't need single head. So this is the multi-head attention part. I will execute this as well. Then I will execute the feed forward network. I'm not going to test them. Okay, we have already tested them. So this is again, and then the transformer block. Okay, and this is where I am basically stacking these transformer blocks. Here I'm combining everything. Okay, here I will just execute this to test our final model is ready. Okay, yes, this is, so this is now our object, my model. Okay, I will be using this to perform the training. Okay, so first thing first, this code. Okay, I'll just quickly explain this code. This tokenize function does nothing but gets the data set. Okay, it passes it to this function. Here it performs the tokenization on this and returns the input IDs, attention mask. Okay, so if I just show you this data set for now, so it has just text and label. Okay, now I will show you after this function execution. Here I'll just print the tokenized data set. Okay, yeah, so the mapping is done. If I now show you guys the tokenized data set, you can see now we have this input IDs, token type IDs, and attention mask. Okay, so now against each text example, we have its input IDs and the attention mask. Okay, so this is what this function is basically doing. Okay, I do not need this token type IDs for our task, and I also do not need the text, like the original text. Okay, I will just be passing this input IDs and the attention mask, and to the loss function I'll be passing this label. Okay, and I'll maybe I need these labels in some other parts as well. So these three are important columns: label, input IDs, and attention mask. Okay, so I'll just remove the text and token type IDs. Let's just remove this. Okay, and now if I show you this tokenized data set, okay, so it has now just the important columns. Okay, here is setting format to torch. What it means basically, so let's say if I for now show you tokenized data set, and in the tokenized data set I have the train split. Okay, from that train split, if I just take the input IDs, okay, so I'll take the input IDs and I'll just take the first input ID. Okay, if I just execute this now, I'll just get its type. So it is a plain Python list. We do not want a plain Python list. Okay, we want to have a tensor. Okay, so we just call this line, that is the set format to torch, and we will have, then this will give us the tensor instead of this. So I'll just copy this. Okay, I'll simply execute this part and I'll just show you the result now. Okay, so if I just check it now, okay, so this is the error that I am getting. Okay, so I will just, I don't need this torch vision. I'll just cut this from here. I'll just paste it over here. If you get the same error, you can just fix it to the false. Okay, so just execute this. Now I'll just test it. Okay, so now you can see previously it was a list. Now it is a torch.tensor. Okay, and that is what we are going to need. Okay, so every time when we will be extracting this input IDs or the attention mask, we will get the torch.tensor. So we will have a tensor rather than a plain list. Okay, now here is this data loader. Okay, let me show you something from the dataset and data loader. Okay, let me open this. This is basically data sets and the data loader. Uh, let's see this part, creating a custom data set for your files. Okay, so what we do, we just create any class. Okay, and we inherit this class with the data set. Okay, we pass our data to the constructor. Okay, like our features and labels. Okay, then we have this length and get item. Okay, this length will whenever we call this length, it gives us the total number of examples. Okay, in our data set. So you can see this length in, and this get item is used by the data loader then, where it basically if we just pass the IDs like the index values, it gives us in return the features plus the labels. Okay, so how we use it, I think there must be some part where the data loader will be calling it. So here is the data loader. Okay, so this we can import from this torch utils data loader. This data loader takes the training data, the batch size, okay, and the shuffle. Okay, so whatever we have like in the training data. Okay, so that training data set, we will pass it to the data loader, and similar task I am performing here. Okay, so I am just calling this data loader. Here I am passing the uh, tokenized data set train, and batch size I'm just giving it 16, and shuffle equal to true. So shuffle equal to true means, let's say in, for example, we have 10 features, let's say. Okay, these 10 features are, let's have this 10 by 4. Okay, so let's say we have this tensor 1.1, 1.2, 1.3, 1.4, 2.1, 2.2, 2.3, 2.4, and till 10.1, 10.2, 10.3, 10.4. Okay, so what shuffle equals to true does, it basically shuffle all these indices. Okay, so your features may be stored in the data sets now. For example, the order changes to the second index row comes to the first. So we will have the first index first of all, then we will have the, let's say, third index, then the ninth index, and maybe finally we have the index 8. Okay, so this index values basically get shuffled. Okay, so now when we have a batch size of, let's say, 2, and we call this uh, data loader data set get item method with batch size of 2. So what will happen in case of shuffle equals to false, we will get these 2 like with the original sequence. Okay, but with shuffle equals to true, okay, we will get this 1 and 3, rather than these 2 rows. We will get the first row and the third row instead of 0th and first. Okay, so this is simply what this shuffle equal to true does to the data set. Okay, same we are going to have for the evaluation. Okay, so each time we will have a batch of 16 examples. Okay, I'll just quickly execute this, and here let me just show you. See, this is where I am just getting the first batch from this. Okay, and let me show you the keys. Okay, so each time in each batch we are going to get label, input IDs, and attention mask. Okay, and if I just show you something, let's say batch this input IDs. Okay, and I'll just simply run it. You can see we have these input IDs. Okay, and if I just print the shape of this, you can see we have 16 input examples, and each input example has 128 tokens. Okay, same if I just look into the attention mask shape, it is also 16 128. And if I simply check the labels, okay, so this label is going to be 16 labels. So against each sequence of 128 token, we will have this one label, true label. Okay, now we are going to choose the loss function and the optimizer. Okay, the loss function that we are going to use is this cross entropy loss. Okay, and the optimizer is Adam W. Okay, you can see this is how we can get this cross entropy loss. Okay, and it by default has these values. We will keep them as it is. Okay, if you look into the parameters, okay, so these are optional, okay, and we'll keep them the default values, okay. This is the AdamW, okay, and if you just look into the parameters here, this is the params, okay. So all of the parameters of our model we are going to pass to this optimizer, okay, plus all these learning rates, betas, or these optional values are also here. So we will just pass the learning rate of our own choice, okay, and we will keep the rest as it is, okay. So let me just come here, okay. So my model dot parameters will pass all the parameters to the AdamW optimizer, okay. Secondly, we are going to pass this learning rate like 0.00002, yeah, that is going to be our learning rate, okay. I'll just quickly execute this. Let me show you the print loss function. This is the cross entropy loss, okay, and the optimizer is this AdamW, okay. So let me see if we have our, yes, this is our learning rate, yep, it's fine, okay. I'll quickly just delete it, this cell, okay. Now the next part is where I am going to put the model to GPU, okay. So if I just show you this part only, here you can see it gives us CUDA, okay. So we enabled our GPU, okay, and now we are going to with this line my model dot to device, okay, we will move our model to the uh, GPU, okay. And let me just cut this line, okay, execute this one, fine, okay, and clear the selected output, okay, just to keep the notebook clean, okay. If I just get this, okay, just this part, let me just copy this and show you what it actually gives, okay. Dot shape, you will now be, I hope you understand this now. So this is the first ever parameter tensor, and that is the embedding layer lookup table, okay, for input embeddings, not positional encodings, okay. So this now gives us the first tensor, and we check the device. If I execute it, gives me CUDA, so it means the model has been properly moved to the uh, GPU, okay. Now the next part is here we will just test the model for one single batch, okay. We will not be executing for all the batches, we will just test it first, okay, with single batch. So this line my model dot train, I'm putting the model on the training mode, okay, to activate all the dropouts, okay. Then here as I mentioned, I will be just extracting the batch, okay, and input IDs from the batch, I'll just move it to the device. Similarly for attention mask and similar for the labels, okay. This is important because on PyTorch we need to have the both the tensors on the same hardware, okay. And plus we also want to execute all these computations on GPU, okay. So we move it to the we move all these to the device, that is the CUDA GPU, okay. Then this is the forward pass, okay. optimizer dot zero grade, as I just mentioned. Okay, uh, we do not want accumulated gradients. Okay, then here with just my model and input IDs and attention mask, just like we tested our last in our last video. So we pass this input IDs and attention mask and we will get our logits. Okay, we just print the logits shape over here, just testing this. Okay, then this loss function will get the logits plus the labels. Okay, and it will give us loss. Okay, and this loss dot item will give us that loss value. Okay, like for each batch there are 16 examples. So this loss, cross entropy loss, if I show you from here, we checked it here. Okay, so by default it has this reduction to mean, so it will give us the mean of all the examples in the batch. Okay, and it will just return us one single loss value, not the 16 different values. Okay, and then this backward, loss dot backward. Okay, it basically calculates the gradients and keep it on the specific variables, okay, where it belongs. And then this optimizer dot step basically updates the values. Okay, so it applies that gradients then. Okay, so I'll just quickly execute it. So you can see this is our loss. Okay, and this was the 16 by 3. We have 16 sentences in each batch and 3 logits against each batch. Okay, like the values against each sentence, against each example. Okay, so 16 by 3. Now here is my randomly initialized model. I'm putting it on the evaluation mode, like deactivating the dropouts, etc. And I'll just test this model with some examples. Okay, because I want to show you what changes do we get, okay, in our model. So initially this is we just put it on the evaluation. This is just for the mapping. Okay, and this predict sentiment takes the text. Okay, converts it into input, embedding input IDs. Okay, attention mask, and with no grade, of course we are not going to update the gradients. We will just calculate the logits. Okay, and then this probabilities and extracting the maximum class, that is the winner class index value. Okay, and then whatever the that index value is, we are just getting the label against it. Okay, and simply we extract the confidence of that specific value in the uh, probabilities. Okay, so it will give us the confidence score plus the predicted class label. Okay, these are some example sentences. Okay, I'll just pass these one by one and we'll calculate the confidence plus also the prediction. Okay, so here I'm just looping over this and printing it. Okay, calling this function. Very simple, very easy. Okay, I recommend if you do not get it, just comment below. I'll answer it. Okay, I'll just execute this and let me show you. So you can see for the, I absolutely love this new phone. It is amazing. It is neutral. Okay, it says it is neutral and 0.5. So you please notice all these values. Okay, this is the worst service I've ever experienced. It says it is neutral. So because these are not the trained weights, we are just testing the randomly initialized weights. So that is why it just gave us any kind of logit. Okay, and now for the 3 epochs we will execute our training loop. Okay, I'll just quickly explain what we are doing here. So we are executing for number of epochs for the outermost loop, okay, putting the model on the training mode. Total train loss equals to 0. Like for each epoch, it will calculate the total train loss, okay. This total train loss equals to 0 for each epoch, okay. Then we loop over this train data loader. Each time we get a batch and the step with this enumerator, okay. So for what we do, for each batch we get the input IDs, attention mask and labels. We put them to the device. Logits we get with the my model call, okay. And this loss calculation, okay, loss dot backward, optimizer dot step and optimizer dot zero grade, okay. Here we just add the loss of each batch to this total train loss, okay. Every 200 steps we want to see the progress, okay. And what progress we want to see, this is the progress, okay. Epoch step of what of this, okay, train data loader length, okay. And then this loss dot item output, okay. So the loss at that specific step, okay, we want to see that. And here the average train loss is going to be the total train loss divided by the train data loader length, okay. So here we are basically calculating the average training loss for each epoch, okay. This is, you can see out of this first this all the batches, okay. So the epoch time we are going to just calculate, and we are going to print this for each epoch. Once we will be printing this, where we print the epoch value. Like for 0 we are just giving it 0 plus 1 to make it feel more natural, okay, starting with 1 and then 2 and then 3, okay. So first epoch finished, and average train loss, we just print the average train loss, we calculate it over here. Very simple, okay. And this is the time taken by this each epoch, okay. Then this my model dot eval. So here once we are out of all the training batches, we evaluate our model, okay. And we do this evaluation on the eval data loader, okay. So total evaluation loss, correct predictions, total predictions, we use these to print the accuracies and loss, okay. So I'm not having any separate function for this. You can make a function and you can call that function, okay, but I'm just printing it right here, okay. And here we just call it with torch.noGrade, no gradients calculation. Each time we get a batch, okay, and that batch basically we all get all these values, we pass it through the model, we calculate the loss, okay, and total average loss again we add it here, okay. Then we get the predictions, okay. So against the predictions we get the argmax, like the maximum index value for 3 logits. In each example we get the maximum index value, okay. And then we just compare it element wise, okay, with the labels. It will just create the boolean vector that gives us true if this condition is true, and if the condition is false it will just give us 0, okay. And we just sum it with the help of sum. We consider the true equals to 1 and false equals to 0, okay, and it will give us simple the integer value, okay, in of Python, okay. And then we just store the correct predictions in this variable, and then the total prediction will be equal to this, okay. We just keep on adding them, okay. And once we are out of this, we basically calculate the average evaluation loss, similarly like the training loss, okay. And accuracy we can see here now, the total number of correct predictions divided by the total number of predictions. Okay, so it will give us the accuracy score. Okay, and if you just search it, the formula for accuracy, you will see this. Okay, finally, then here just printing it. Okay, the validation loss, the validation accuracy for that epoch. Okay, and once this is done, we will be then moving to the next epoch. Okay, so this now I'll start the training of this, and once this is done, I'll resume the video. Okay, so yep, it has been started. Okay, so I see you once it's completed. Okay, so our training is done. This is the result of our training loop. Okay, so you can see at every 200 step we are just having this logs. Okay, and after each epoch we are having the average training loss. Okay, then the time taken by that epoch. Okay, and then the validation loss and the validation accuracy. Okay, so it started with this average training loss 0.91. Okay, and then it came down to 0.82, and at the end of third epoch it came down to 0.7790. Okay, and the validation loss is 0.83684. So it started with the 8959 and it came down to 8368. Okay, and accuracy you can see 5675, then 60%, and then 63. So this is the final result of the third epoch. Okay, so now I will just put the model on the eval mode. Okay, and I'll execute the same testing again. Okay, if you remember, we executed this testing before training our model. Okay, now we are again executing the same code, okay, with the same examples, and we will see the difference, okay, this time. So let's execute this now. Okay, so first you remember it, for every example it said, let me just show you that. Okay, I think it was somewhere, yeah, this one. Okay, I'll just copy this cell output. Okay, and I'll just paste it over here. Okay, and we will then compare it. So for the first sentence, I absolutely love this new phone, it is amazing. Okay, so you can see previously it said neutral, confidence equal to 0.527. Now after 3 epochs it says positive 0.995. Okay, and the second sentence is, this is the worst service I've ever experienced. So previously it said neutral and this, so it was raw score. Now it says it is negative. So previously all these raw scores, okay, neutral and raw confidence score. Okay, but now you can see the model has learned a lot, okay, with just these 3 epochs and the limited data set. So this model uh, has no previously pre-trained weights. It is just simply the randomly initialized weights. We have trained them. Okay, the meeting is scheduled for 3 p.m. tomorrow. Okay, it says it is neutral, confidence is this. Okay, I'm not sure how I feel about this, it's kind of mixed. Okay, so see, this is a kind of confusing sentence. It gives us this kind of confidence score, and it says this is positive. Okay, wow, absolutely incredible experience, would recommend to everyone. Positive, strongly confident on this. Okay, I'm not feeling good, so performing a little bad on this, but with low confidence score, so not that much bad, like it is not that much confident that it is positive. Okay, so this is the result of our training. Okay, I just want to now stop here, and we'll cover the saving of these weights and loading again and testing it in the next video. So this is all for this video. I hope you enjoyed the video, and if you have any question, you can ask me in the comments and I'll answer you. Okay, till the next video, bye bye.